All right, so let's have a look at the actual experiments themselves. So I'm going to assume that you've downloaded and got the program going just following those instructions. That's all I've done so far, and I had a bit of a fiddle around with the program, so I know what I'm doing with it. So let's have a look at experiment one. So we're in the electromagnet tab, so this one here, and I'm just going to reset everything, make sure it's back to its default. So what we could see here is we've got a cell providing a DC current because all the electrons keep going in the same direction at the same rate all the time. And as with any magnetic field around a solenoid, we can see through the middle we've got what we'd call a uniform field or a constant strength field through there. But you can see that when we're on the outside, the field becomes curvy, like you can see around the edges here. So let's see what our actual instructions are. So it wants us to show the field meter. We're not going to worry too much about what the units of this are. It's Gauss. There are actually loads of different units you can use for the strength of a field. But we're just going to try and compare it qualitatively. So like in words, we're going to see what things affect how strong the field is. Okay, so let's do that. Show field meter. So it says it should be 302, 302, 0. Yep, looks good. We're only interested in the BX value, so we're interested in this particular one here. Okay, cool. Okay, so we don't want to move the battery or the field meter, okay, because otherwise they'll affect the results as well. But we can always put it back if we want to. So vary the number of loops from 1 to 4 and record our results. Let's start at the bottom. So you can see at the bottom, we're recording BX. So with number of coils 1, that was 0.76. Number 2, with 2 coils, we've got 1.51, which I'm already spotting is double what it was to start with. So this is looking sneakily like a directly proportional relationship. Looking very like a directly proportional relationship. And then with 4, we've got, what am I doing? 3.02, which again, going from 2 to 4, we've actually doubled our field strength. So that is looking very like a directly proportional relationship, and it's going to be annoying and not let me cut this box, which is irritating me. Oh, whatever. So those are our results. So what I'm seeing here is if we're essentially doubling the number of coils, we're doubling the strength of our electromagnet's magnetic field, and we've got a directly proportional relationship here. So I'm just going to record that in the results at the end. So what we're seeing is it increases the strength of the electromagnet, and I think we should add in the extra detail because we've got a bit more data. It seems that so it's directly proportional to the number of coils. Okay, so let's go back and have a look at this. So it wants us to reset everything, so let's do that. Okay, so the simulation does not have a readout of current in the coil, so we'll use V equals IR to calculate this. Assuming the resistance of the coil is 10 ohms. In the table results, fill in the column for current at each different voltage. So basically, using V divided by R, we're just going to divide all the numbers by 10. So that's going to be 1.0, 0.9. I wish this was on Excel. I could make it do it for me, but so be it. God, this is tedious. Okay, there we go. So we've got all of our currents by dividing all our voltages by 10. Okay, so using the simulation, turn on the field meter. Great. Okay. Vary the voltage, and hence by varying the current, record how strong the field is. Okay, so our current here is currently terrible wordplay. Okay, so our current to start off with, remember, was 1 amp. We can see the field strength is 3.02. Then our current is 0.9. And we can see this is cut to be 0.02. To be honest, I don't see the value in collecting all these midpoint data, so let's just jump to 0.7. Let's speed this up a little bit, 2.17. What I'm particularly interested in is what it is at 5 volts, where we've halved the current, 1.55. So you'll notice here, halving the current seems to have pretty much halved the field strength. Let's jump down a little bit more. Let's go to 0.1, 0.31. If we put this on 0, there is now no current. And so because no charges are moving, we can see that there is no magnetic field. That shouldn't be too shocking. Let's put this now on minus. So we've got minus 0.2. The magnetic field strength is now a minus number. So actually, what that means is that our field is now in the opposite direction. So let's jump all the way up to 5, so we're not wasting time. Minus 1.55. So the thing to spot here is you'll see that when the current is minus 0.5, so our current is in the opposite direction, but the same number, the field is just as strong, but the field is in the opposite direction. So let's go all the way up to minus 1. Oh, and Kelspries, we've got minus 0.10. That's interesting that it's slightly different to that one. Let's put that all the way back to their end. Did I write that down wrong? I did write that one down wrong. Okay. So what we can see there is what we look like. We've got, again, it looks like we've got directly proportional relationship, and that changing current direction changes the direction of the field strength, but it doesn't change the size of the magnetic field strength. So I'm guessing there's a place to write our conclusion. Okay, so and then let's put in our additional detail. Okay. And when we change the current positive to negative, the direction of the magnetic field changed. And you actually see that with these arrows. You can see here, this arrow is pointing to the right. If I flip this, you can see the arrow is pointing to the left. So we've flipped the direction of the magnetic field there. And it says not including the simulation. We can also try inserting a soft iron core or any other soft magnetic material into the center of the coil, and what that does is it aligns itself with the magnetic field, and it makes the electromagnet even stronger once it's aligned itself with the electromagnet's magnetic field. So that would also allow us to make the magnetic field even stronger. And I'm just going to add a little bit on the end, because there are some ways of figuring out. So if you have a magnetic field, you can work out the force that it will exert on things, and what it turns out is it's directly proportional to things like current and its and magnetic field strength and stuff. But that should do us for this experiment. We've got these key ideas that the strength of the field is directly proportional to the number of coils and to the current, and that changing current and causes a change in the direction of the magnetic field. So that's given us the key ideas that we need.